Bioinformatics Micromodules, suffix trie. In this module, we introduce a basic concept about suffixes commonly used to perform text search, and a simple indexing structure called the suffix trie that makes use of this concept. First of all, let us recap the meanings of the terms prefix, suffix, and subsequence. Suppose you are given a sequence S of length n. A prefix of S is a beginning part of it, or the empty string. You can also think of a prefix as cutting out 0, 1, or more characters from the n, with the extreme case being cutting out all characters, which gives the empty string as the result. Similarly, a suffix of S is an ending part of S, or the empty string, which can also be understood as cutting out some characters from the beginning of it. Finally, a subsequence of S is the middle part of it from the ith character to the jth character, or the empty string. In other words, a subsequence is the result of cutting out some characters from the beginning and some characters from the end. Let's see an example. Suppose S is our famous tat-a-cat tag. The full set of suffixes is shown here. If we use the square bracket notation introduced before, the subsequences are S1.10, S2.10, and so on, until S10.10, and also the empty string. This empty string case is a bit troublesome because it is not clear how we should represent it using the square bracket notation. Some people use a special symbol to represent it, while some others use a starting index 1 larger than the ending index to represent it, which in our case is S11.10. This is somewhat counterintuitive because naturally you would expect the starting index of a subsequence to be always smaller than or equal to the ending index. To deal with this issue, let us introduce a special end of sequence symbol $. For the remaining of this micromodule and the coming ones related to short read alignment, we will always add this $ symbol to the end of the reference sequence. With this symbol added, we now have a more natural way to represent all suffixes of S, which are S1.11, S2.11, and so on, all the way to S11.11, and this last case represents the empty string. After talking about prefix, suffix, and subsequence, now we want to relate these three terms by a simple yet powerful concept. The concept is that every subsequence is a prefix of a suffix. If you do not find it obvious, let's consider the subsequence ACAT of S. If we list out all suffixes of S, we see that ACAT is at the beginning of the fourth suffix of S. In other words, ACAT is a prefix of this fourth suffix of S. In our application of short read alignment, this concept states that a short read R is a subsequence of reference S if and only if R is a prefix of a suffix of S. Therefore, one way to check whether a short read has a perfect match with the reference is to find an index such that the prefixes of all the suffixes of the reference can be looked up efficiently. One such index is the suffix trie. The term trie is not commonly used. Basically, it is a tree, but we use the term trie here because later we want to introduce another indexing structure called a suffix tree. The main difference between them is that a suffix trie allows an internal node to have only one child, but the suffix tree does not allow it. Let's use our famous reference sequence tat-a-cat tag to illustrate what the suffix trie is. Here, you see all the suffixes of sequence S on the left and the suffix trie on the right. Basically, you can imagine that the suffix trie is constructed by inserting each suffix from the root down the tree. For example, the first suffix is TATA CATTAG $. And correspondingly, we can see this path that goes down the root first to a T node, followed by a node, and then T, A, C, A, T, T, A, G, $ until the leaf. We repeat this process by inserting every suffix to the suffix trie. During this process, if we find that a node that we need has already been created previously, we just reuse that node instead of creating a new one. For example, the third suffix is TACA TTAG $. When we insert it to the suffix trie, since there is already a T node, which is a child of the root, and an A node, which is a child node of it, we do not need to create these two nodes anymore, but just reuse them, followed by the remaining nodes that we need to create. Before moving on, there are two more things that we should mention. First, if a node has several children, we order them alphabetically from left to right, and the $ symbol is always ordered before all other characters. For example, in the suffix trie here, the root contains 5 children, and we order them from left to right alphabetically, representing $ A, C, G, and T. The second thing to mention is that here we attach the character labels to the nodes, but equivalently, we can also attach them to the edges. For example, here there is a child node of the root labeled $. We can also put this $ label to this edge that connects the node to its parent instead. Now let's see how we can do text search using the suffix trie. The idea is very simple. Starting from the root, we look for each successive character in the query from the children of the current node. If we successfully do that for every character in the query, then it is a subsequence of the index reference sequence. Otherwise, it is not. For example, suppose we want to search for ACAT. Starting from the root node, we first ask whether among the children of the root there's an A node. The answer is yes, so we move there. Then we ask whether among the children of this node there is a node that corresponds to the next character of the query, which is C. The answer is also yes, so we move there. In the same way, we next look for A among the children of this node, and then T among the children of that node. Now we have exhausted all the characters in the query, and therefore we conclude that ACAT is a subsequence of the index reference sequence. Once again, this is because we have confirmed that ACAT is a prefix of one of the suffixes of the reference sequence. In short read alignment, we also want to know the location of the short read in the reference. In order to answer that question, we will need to record some positional information in the index, and we will leave the details to the next micromodule when we introduce the suffix tree. Now let's see another example. Suppose we want to search for CATC. Starting from the root, we find a C node among the children of it, and so we move there, and then an A node, and we move there, and then a T node, and we move there. But now we do not have a C node among the children of the current node. Therefore, we conclude that this query, CATC, is not contained by the reference sequence because it is not a prefix of a suffix of it. Finally, let's perform some complexity analysis. When searching for a short read of length m from a reference sequence of length n, in the worst case, we need to visit m nodes after the root node. Suppose checking whether a node is present at the next level can be done in constant time, which can be achieved if we have a fixed alphabet, such as the alphabet of $ A, C, G, and T for DNA sequences. The time complexity of the whole searching process is order M. This is very good because it is unrelated to the length of the reference, which is much longer than each short read. As for space complexity, for a reference sequence of length n, the suffix trie has a worst case size of order n squared. This is unacceptable because n can be as large as several billions. In the next micromodule, we'll study how this space complexity issue can be handled by compressing the suffix trie into a suffix tree.